Welcome back. In this lecture, we will describe the k-nearest neighbor algorithm. So here's our objective. Now, k-nearest neighbor is still a supervised machine learning approach. It is a non-parametric method, meaning that it is acting on the data, on the historical data, as it makes inference. And so because of that, it also can be considered supervised because it's still using that training data, as part as a key component for making inferences in the future. Now, k-nearest neighbor directly uses what is called a distance function. And in this lecture, we will refer to the Euclidean distance, which is the most common. As a quick refresher, it's simply applying Pythagorean theorem between 2 points in the feature space. But notice that it is generalizing Pythagorean's theorem for m number of features as opposed to just 2, like what's shown in the picture. So this is a very straightforward algorithm, honestly. You have some new sample x. It's not in the training data. And what you do is for each x prime in the training data, you calculate the distance to it. And then out of all that training data, you just identify the top k elements of the training data that are closest to x, so where that distance is the smallest. And then you just assign x a class label from the majority of those top k elements. And that's kind of it. So all it's doing is it's comparing your new sample directly using a distance function to everything in the old data that you were using. Now selecting k is a hyperparameter. So just because it's non-parametric doesn't mean we can't have hyperparameters, so please bear that in mind. And so you can figure this out by optimizing an error metric using a validation set of data, which is a common way to identify hyperparameters and using something like, say, beam search or something like that. Common issues, very small values of k, they're of course going to overfit because it's, so if you think, for example, if k equals 1, it's just going to go to the nearest possible thing. And of course, if you have larger values, the larger the value of k, especially as it approaches the size of your population, that's just going to give you the prior probability of the class. So if you could imagine that if you had a very large population of people and you were trying to predict if a new sample was like, say, a tweet or something, if it was made by a man or a woman, and you would do k-nearest neighbor with almost the entire population, it's going to give you results that would just reflect the split of those two classes, the fraction of the population that are men or women. So that's what is meant by underfitting. It starts to reflect the prior probability. The normal range that in practice that's often used is between 1 and 20, but honestly it's going to depend on the size of the training data, the balance of the training data, as well as the number of classes. And one other thing about selecting k, in general, especially if you're picking a smaller number, you probably want something odd because that's going to help avoid ties. Now, a key thing to note when using k-nearest neighbor is you may have to scale your feature values, because you could imagine that if you have two different scales of feature values, you could have outsized importance for one or the other. And so scaling, ensuring that it falls within a certain range, there's actually a couple different ways to do that. So first is clipping, which is just saying, hey, if my value is above or below a certain value, I'm just going to stop it at that. So if we have age and we want to clip our age range to be, let's say in an example like this, between 20 and 30, You have someone who's in their 80s, they're going to be treated as a 30-year-old. You have someone who's a teenager, they get treated as a 20-year-old by the algorithm. Another thing is logarithmic scaling, and this you just take the logarithm of the feature value, and this is useful when you have something distributed with, say, a power law distribution. So, for example, number of connections in the social network. There is a very small number of people in a social network like Twitter or Facebook that have a huge number of connections. And so that can really distort, algorithms like K nearest neighbor if you want to apply it on a population across people like that and use something like number of connections as a feature. Now, if you apply the logarithm to that, you have really done a lot to bring the range of that value, that feature, in a much tighter, range, as opposed to if you did not do that. Z-score deals with using the mean and standard deviation of the values, and so now you're just scaling it by standard statistics using the Z-score. So which one of these to be used really kind of depends on the characteristics of the data itself for that particular feature. And you can even scale things, scale different features in the same problem differently. Give you example, if the data for a given feature follows a normal distribution, it might be sensible to use a Z-score. If the distribution of data for your feature is a power law distribution, logarithmic scaling might make sense. If the distribution of your features, when you draw a box plot, the box is compressed in a very tight range but has very far out whiskers, then clipping would potentially make a lot of sense. So anyway, this concludes our discussion on K nearest neighbor. Please stay tuned for more content.